I welcome you once again to this class of microscale transport process. In the last class, we have been discussing mixing and more importantly mixing quality and mixing effectiveness, right. In the last class, we defined a term called alpha. We defined a term called alpha, which changes from 0 to 1 in the mixer. Alpha is equal to 0 at the inlet when the flows are considered completely segregated, and alpha is equal to alpha should be equal to 1 at the end of the at the outlet, so that you can consider mixing to be complete. So, this is a term which is basically the mixing, what we define this as mixing quality. So, if I have a stream and if somebody says that how good is this, how good the mixing has been done, so this alpha is a good parameter for that. However, the other term that we are interested in here other than mixing quality is what you call mixing effectiveness. Mixing effectiveness, that means how effective the mixer is, because you know that if we have two streams flowing side by side, okay, so at some point they will all mix. I mean, maybe it will take 1 centimeter, maybe it will take 1 meter length, but at some point of time it will be completely mixed. So, you can always realize alpha is equal to 1 at some length, but that is not exactly the objective. Objective is to minimize the length, right, because you have to minimize the length, and not only minimize the length, you have to see how effective the mixer is in terms of pressure drop, because you can have a very short length and you can achieve the mixing. However, you may encounter a good amount of pressure drop, and then that would be a deterrent, because you can only have so much of pressure drop. You remember when we worked with these microfluidic devices, we had those inlet and outlet fittings, right. We have a capillary tube which goes into the this microfluidic device, okay, and then how we arrange the sealing. We put a plastic coupler, we put a press fit arrangement. We have worked with so many arrangements, and some arrangements, for example, the press fit one. At the very outset, we said that the press fit one is good. I mean, you can just push it and it goes in there, but it can hold only to certain pressure. Beyond some pressure, it will start leaking from there. So, if you have a huge pressure drop within the micro channel, that means at the inlet port, the inlet port would be exposed to a very high amount of pressure, and you cannot afford that, because then it will start leaking. I mean, it is a very simple, very trivial problem. So, the pressure drop should be I mean, you have to keep an eye on the pressure drop. So, you have to define mixing effectiveness such that it gives you highest amount of revenue for a given effort, right. So, that's the idea of mixing effectiveness. So, we have this mixing effectiveness defined as this mixing effectiveness is defined as revenue divided by, that is what level of mixing you achieve divided by the effort you expend. All right. Now, there is a term called Euler number in this context. This is typically, this Euler number is used in connection with vortices. If there is a vortex, the amount of pressure drop that you have to expend, that you have to provide is given is defined in terms of Euler number. This Euler number is nothing but delta p. If there is a vortex element involved, then delta p v divided by rho w bar square, where w bar is the average velocity, and delta p v is the pressure loss caused by vortex creation. So, this is the Euler number associated with the vortex, and that is how you define Euler number is delta p v divided by rho w bar square. Now, you can in fact talk about specific energy dissipation . Specific energy dissipation, which is defined as delta P v, the pressure drop, multiplied by volumetric flow rate divided by mass into which energy is dissipated. Okay. So, then in that case you can write this as delta P V. If cross section of this mixer, you write this as A m. So, volumetric flow rate would be A m into W bar divided by mass into which this happens. So, it is rho A m and L m. L m is nothing but the length of the mixer. So, this comes to be equal to E u v Euler number. The Euler number, if you can have a small subscript as v, Euler number associated with the vortex W bar cube divided by L m. So, this is the specific energy dissipation. So, this is the amount of energy that is getting dissipated in this context. So, now if you define the mixing effectiveness we said is revenue divided by effort, all right, revenue divided by effort. Now, what is the revenue here? We can write that this revenue is higher if shorter mixing length at a large hydraulic diameter. Okay, so, if you have a shorter mixing length, it would be higher if shorter mixing length at a larger hydraulic diameter. Okay, so, this is how we have this is the idea that we have as far as revenue is concerned. So, in that case the revenue divided by effort, and the effort is basically, the effort would be, we can write this as the Euler number itself. Okay, so, this mixing effectiveness, now we said revenue is higher if shorter mixing length at a larger hydraulic diameter. So, this revenue then in that case is equal to dH hydraulic diameter divided by mixing length. So, that this revenue, in the sense that if you have a shorter mixing length, then the revenue would be higher, and if you can do it for a large amount of stream, a large volume of stream, that means if you have a higher hydraulic diameter. So, this is how you are defining the revenue, okay, such that revenue is higher when you achieve mixing in shorter mixing length for a large volumetric flow. So, that is how you are defining revenue. Now, one thing you must understand is that this L m is nothing but W bar into T m, okay, and A m, this is of the order of dH square, hydraulic diameter to the power square. I mean, that is how the hydraulic diameter is defined. I am not saying it is equal, but it is of the order of, and L m is W bar into T m. Okay. So, in that case T m is the mixing time and W bar is the average velocity. So, in that case mixing effectiveness, this M e is defined as m dot, the mass flow rate, divided by hydraulic diameter delta P into T m. Okay. So, this is what you define as mixing effectiveness. In some cases they multiply a Reynolds number to this, but I am not getting into that. Let us focus on a mixing. This is a standard way of thinking about mixing effectiveness. Now, I mean it is open to debate. I mean, you can add or remove some terms, or you can improve the mixing effectiveness, but this is one standard way of defining mixing effectiveness. Okay. So, what all did we define here? I mean, you got to understand that we have these. I mean, if somebody sells a mixer, if somebody makes a mixer and somebody wants to sell that to you, what will you ask from him? Okay. One thing you may ask is that, okay, if I have this is the stream. I mean, I define the stream. What would be the mixing quality, that index alpha at the outlet? That could be a way of looking at it. I mean, you can ask for it. You can find out what is Euler number, or you can find out what is the mixing length, LM, or more importantly, you can ask him what is ME, what is the mixing effectiveness. So, these are some of the parameters you can ask from him, or you can expect that they will provide these parameters. A person who is making a mixer and who is selling to you, you can expect that they will provide these factors. So, that if you have to make a comparison, okay, I have a choice of say 4 such mixers from 4 suppliers, which one I should purchase. So, these are the parameters that will guide your decision. All right. So, this is, I mean, you just have some thought into it, that there should be some parameters, some guiding parameters to decide which mixer is more effective in your situation, and this is how it is done. Okay. Now, it is open to discussion, and you can add or remove terms. I mean, if you think that is more pertinent. However, this is a framework that people have already thought about, the researchers have already thought about. Okay. So, with this I am not, I mean, with this I practically complete the discussion on mixing. Okay. The next topic that I pick up. So, let me recapitulate what all we have done. We have defined various kinds of mixers. Okay, segmented flows, sequential injection, then having herringbone type mixers. In fact, that description is on the slide itself. We have discussed about having grooves on the floor, and then we have cross flow. We are inducing cross flow, and then we are intentionally shifting the center of the helix from left to right, so that you have the cross flow very effective. You have the cross flow helping you accomplish the mixing. We have talked about various mixing strategy. At the very outset, we said that if we had 2 streams flowing side by side, then also we can expect some mixing because of diffusion, but that will take a very long channel. I mean, the channel has to be really long. It is 1 centimeter to 100 centimeters. It's that way. We have already shown using some dimensionless numbers. So, naturally that is not the way to do it. So, you have to induce some amount of cross flow, and that cross flow can be induced this way, or it could be that you have an on off type situation, solute then solvent, then solute then solvent. So, you can have that kind of situation as well, and I more or less we are governed by the mass balance equation over a differential element using diffusion coefficient. That has been the governing equation. However, we used it in different context, and I showed that you can, I mean, if it is a completely unknown mixer which you do not have any guiding principle, you can probably give some you can give it, I mean, you can define a stretching function, and you can probably I mean, I have shown that there would be 2 limits. One is the Peclet number and the log of Peclet number, and you will be in between them, whether you are in linear stretching or elongational stretching. So, you have some way of characterizing a mixing process or characterizing a mixer. So, by now you should have fair idea how to get this done. Next topic that I pick up now is known as Taylor dispersion. Okay. This is you remember when we were talking about that on off mode of mixing, there we have, instead of a diffusion coefficient, I mentioned dispersion coefficient, and instead of D I have written D star. There is a reason to it. I mean, this when we talked about a spot of tracer diffusing into an infinite medium, we restricted ourselves to diffusion coefficient. However, when there is a flow as well as diffusion, then we have to take some additional terms, and then we call this process dispersion rather than diffusion. See, the first if you look at this slide, this Taylor dispersion, there the first topic is dispersion is flow plus Brownian motion, which is equal to rapid mixing. So, diffusion is basically the Brownian motion, only the by molecular interactions some particle is diffusing into the medium. But if you have a flow associated with it, then you call this a dispersion. A good example would be smoke from plume carried by wind velocity. So, what do you have in a plume? I mean, you have smoke coming out, and then that smoke is being carried by the wind velocity. So, the smoke is diffusing. Smoke is diffusing. I mean, if there was not any wind velocity, if just the smoke is being released there, so smoke would be diffusing gradually, that you know. But since there is a wind velocity, so smoke is further carried downstream. So, you are having a flow as well as diffusion, and this is a classical problem of dispersion. All right. So, you must appreciate the difference between a diffusion and a dispersion, that is the third point. Now, dispersion of tracer while flowing through a canal, whether circular or non-circular cross section, that has small transverse dimension, that is what we are interested in, and that is referred as Taylor dispersion. What is that now? Suppose you have a flow going on, all right. You have a flow going on and you have a parabolic velocity profile. So, this Taylor dispersion, mind it is important in a micro channel when the transverse dimension is small. If it is a big channel, I mean a large diameter channel, absolutely that is not this is not at all a problem, because there you will have a potential flow. I mean the effect of viscosity would be less, it would be a potential flow at the center. Okay. So, this problem may not be important at all. Suppose this is a parabolic velocity profile and you have you give a pulse. So, suppose this is the pulse. This pulse is injected. You understand how a pulse is injected? I am little shifted here. You understand how a pulse is injected. That means, I have a tube through which water is flowing, okay, at constant velocity. The dimension of the tube is very small. It is a very thin capillary. You understand what a capillary must be? It is an advanced level course. I mean the capillary, ideal example of a capillary would be what you see inside a thermometer. That thin tube through which the mercury rises, ideally that is called a capillary. It is a very thin tube. Okay. Through that some water is flowing, and it has to be a parabolic velocity profile, because the transverse dimension is really small. If the transverse dimension is like a big channel, I mean if it is 1 meter wide channel, then probably you cannot expect, I mean you may not expect the flow to be fully developed and parabolic and all this. However, this is the case for a small capillary. Now, you are introducing a small amount of dye for a short while. So, it is just a pulse of tracer. That means, you introduce, suppose you put an injection syringe, take an injection syringe and pick up a little bit of colored say ink. From an ink bottle you pick up a small amount of ink and you introduce it at the inlet, just push the piston within a short time and then remove the piston and water flow continues. So, thereby what you give is a pulse. So, this is what you have introduced in the flow, So, now this flow as it goes through the tube, it has to take a parabolic shape. So, what would be the shape of this as it travel downstream? So, it will take a shape like this. Do you agree with this? That this will take a shape like this. This has to, because it would be so what I am essentially saying is that the central part of this block is traveling faster, and the part of the block which is next to the wall is practically having 0 velocity. So, that is how it is flowing. So, now what did you expect if, I mean if it would have been just simply diffusing? How did we work with that? We said that, okay, you remember, I mean let us look at this as a Dirac function. We had a Dirac function, and then we said that this would be, next one would be this one, then next one would be this one, like this. You remember, that is how the concentration will decrease. So, it will be diffusing out, but now the process is completely different, because diffusion will take place from here to here, here to here, here to here, here to here. So, the diffusion process is completely different now. It is not, I mean, you expected the diffusion to take place in this direction and in this direction, right, the way it is for a spot of tracer, but that is not the way it is happening. It is happening this way. All right. Now, if you pick up from the outlet, if you pick up the concentration, I mean, if you find what the concentration is now within a capillary, I do not expect that you will find a concentration distribution in this direction, because this dimension is very small. This dimension is very small. So, I do not expect you to find the concentration distribution here. Rather, at the outlet, what you get is, you pick up a slice, measure the concentration, you pick up the slice next that you receive, then you pick up the slice that you receive next and measure the concentration, which is basically the average of these, average over the entire cross section. So, whatever you receive here, that is averaged over the entire cross section. This is called a mixing cup concentration. I mean, it is like you take that slice, mix it and get the average concentration. That is how you can suppose this is a thin capillary, and at most what you can have is an outlet connected to a detector. So, detector would be detecting, but detector would be detecting what concentration? The average concentration of this entire cross section, that is all it can detect. Now, pick up an average concentration, what do you get here? Suppose I pick up an average concentration of this cross section, I will get some amount of this, which is not the solute at all, some amount of solute and some amount of the other stream, which is not solute at all. So, that is what we will see. If I pick up this one, what do we see? Same thing, some part is solute, some part is not solute. So, think of it that suppose I do not the diffusion coefficient is negligible, close to 0. Still, if I look at, so I have given a pulse here, I have given a pulse here. Pulse is actually not a Dirac function, pulse is, this is a pulse. Okay, so, I have given a pulse here. Okay. So, what do you expect here? Even if the diffusion coefficient is 0, still I would expect this would be what we get. So, what is this? I mean, do you understand what the axis is? Axis is basically time, and this y axis is concentration detected. So, do you understand what we are trying to say here? These pulse, or I mean, if I mean, what was our expectation? Our expectation was that if there is no diffusion or diffusion is negligible, we would have gotten this pulse, the same there, right? If you put something in the water and that is having negligible diffusion to the medium around, so that would remain the same, remain there that way, right? That is what you expect. So, that is what you expect here. I mean, if this would have been if there is a pulse like this, you would have expected what is coming out. So, this pulse means this is the concentration versus time. This is the concentration and this is the time. So, concentration versus time, there is a pulse. So, at the outlet also you should have received a concentration versus time as a pulse, but instead of that you are getting a broadened peak, and this broadening is taking place because of this velocity profile, this parabolic velocity profile. All right, even if the diffusion coefficient is not significant. So, this process, this is what is referred as Euler dispersion, and this is something which you have to be very careful with when you are working with a laminar flow in a channel which has a very small transverse direction. Okay. Now, let me give you the final result. Let me give you the final result. What you get as a concentration profile. I mean, I will try to come up with the governing equation and boundary conditions and everything, but I would first I would like to give you the final expression. The final expression looks like this. here the m is total solute in the phase, total solute in the pulse. R 0 is equal to tube's radius, z is equal to distance along the length of the tube, V naught is equal to fluid velocity, T is equal to time, and E z is referred as dispersion coefficient. So, this is the same thing what we have referred as d star in earlier, and this is the dispersion coefficient, and this dispersion coefficient is equal to R naught V naught whole square divided by 48 d. This is also referred as at times as Peclet number for this dispersion. This is also referred as Peclet number for this dispersion. Now, what do we have here? I mean, if we look at this m divided by pi r 0 square, does this ring a bell? M is the total solute in the pulse, and pi r 0 square, r 0 is the radius of the tube. So, pi r 0 square is the area over which the diffusion takes place. So, you remember when we talked about the diffusion of a spot of tracer in an infinite medium, there also we had a m by a term in the numerator. So, this m by pi r 0 square is that m by a term. Okay, that is one thing I want you to appreciate. The other thing I point out here is this z minus v 0 t term. Does this ring a bell? Z minus v 0 t. Z is the distance. Z is the distance along the length of the tube, or in other words distance from the inlet. So, the tube runs like this, and from the inlet you calculate z, and v naught t, v naught is the average velocity of the V naught is the average fluid velocity, or the fluid velocity means that this is basically the average. Okay. So, because since we have a parabolic velocity profile, so you consider this to be average. So, V naught t is basically the place where it is, I mean where the pulse would have been if it is travelling at average velocity over time t. So, z minus V naught t is, since there is a movement of the pulse, I mean diffusion plus flow, this flow part you can separate if you define a coordinate system which is z minus V naught t. Does this make some sense? V naught t would have been the shift of that center of the pulse because of the flow, okay, and z you are calculating from the inlet, your reference. So, z minus V naught t is another coordinate system where it is a sort of a moving coordinate, the moving coordinate with reference to the center of the pulse, or the place where the pulse would have moved by average velocity. So, z minus V naught t is this term. The other factor that I must point out here is that this dispersion coefficient, here we have E z. This expression is very similar to the expression that we had for a spot of tracer moving into the infinite medium, but instead of E z at that time we had d, I think, diffusion coefficient, but now we have E z. But the most important thing here is that this E z, this dispersion coefficient, this expression, look at this expression, R naught V naught square divided by 48 d. Okay. So, d is in the denominator, and earlier you had E z, this was equivalent to d. So, that time d was in the numerator. So, that means d has an inverse effect, whatever effect d had on the diffusion of a spot of tracer in infinite medium, whatever the d was doing, the diffusion coefficient is doing, here the diffusion coefficient is doing just the opposite to it. Do you appreciate, because d is in the denominator. If d increases, the process is going other way, and there if d increases, the process goes the in some other way. So, this effect of d is completely different, and another factor is that d Ez, which is equivalent to the d, that is dependent on V0 square. So, that means the factor that is responsible for the spreading of solute, the spreading I am talking about, the factor that is responsible for the spreading of solute, that factor is basically that is the spreading is defined by V0, not only V0, V0 square. That means, if you have a higher average velocity, you can expect more spreading. If you have so these are some of the things that you need to similarly, if you have a higher R0, you have more spreading. So, if somebody says that as a matter of fact, this Taylor dispersion is very important in connection with chromatography. Chromatography, do you understand what a chromatography, how a chromatography process works? I mean, we have these HPLC and GC, gas chromatography, and this HPLC. These are typically you have some experiments in master's level. You do some experiments with these instruments. These instruments, here you have, suppose you have A plus B plus C plus D, and you would like to identify which components you have. Suppose you have a sample which has A, B, C, D, and you do not know what these A, B, C, Ds are. So, what you have is you generally, in a conventional chromatography, you flow this solution, or you have a carrier stream going in, and this A plus B plus C plus D, which is the sample, you introduce this in the carrier stream as a pulse, just the way you have done it here. Just the way you have done it here, in a similar manner, you introduce them as a pulse, these A plus B plus C plus D, okay. And then you have this adsorbent. I mean, in a conventional chromatographic unit, you have a packed bed, okay, and this packing on those beads, basically packed bed means it is a bed filled with beads. So, there flow can take place through the sides of these beads. That's the idea of a packed bed. Now, this wall is coated, it has a special coating, and this wall will adsorb. So, when these A plus B plus C plus D, when they are flowing, now they have some preferential adsorption, okay. Maybe this A is adsorbed more, B is adsorbed less, it is that way. So, when the sample is passing through it, it would be immediately adsorbed, and then it would be released at a later time. So, what you see here is at the outlet, if you have a good detector, you would be seeing peaks like this, because one would be eluting at some time, the other one will be eluting later. It depends on adsorption desorption phenomena as far as this component, one of these component is concerned with the adsorbent that is put there, all right. So, that is how it happens, and you see these peaks. Now, in a microscale process, you do not expect the beads to be there. Two ways it is accomplished. One is you have a microchannel with a wall coated with adsorbent. So, the wall acts as an adsorbent, or it could be that you have a monolith, because those that small bed is not very common. You have a monolith structure. That means, you have a structure where, I mean, it is more like a honeycomb. I mean, it is already inbuilt. I mean, this entire passages, everything is built in an integrated structure. It is not like that you take a tube and then take a pack of beads and then fill it there. It's I mean, a good example of beads would be, and filling of beads would be, if you have been if you have seen these water purifier that we have in household water purifier, they have a resin bed, and they every 6 months probably they are supposed to take that bed off and put new ones. So, those are the small beds, okay. But in a microscale, you cannot afford to have a tube and then fill it with beads and all this. So, you have a monolith structure like a cartridge, you have that inbuilt channels inside like a honeycomb, okay. So, these chromatographic units are very helpful in separating these components and then detecting, and you have to, of course, you have to first calibrate it. You have to send known samples and see where how the peak appears, and then review that with reference to what you got for a real sample, and from there you can come up with what all components are there. Now, you should be expecting, you should be getting these peaks, and each peak is referring to A, B, C, D. Now, if you have this problem going on, if you have this dispersion going on, what will happen to these peaks? This will not be a sharp peak, rather this will be a diffused peak like this. This would be another diffused peak like this. There would be another diffused peak like this, because it would be broadened, right? The peak would be broadened because of this effect. Okay. Now, if because of this broadening you miss out a peak, it could be possible that two peaks get merged and you do not get the peak at all. So, when you work with this process, it is absolutely important that if this look at this dispersion coefficient Ez, D you do not have any control over. D you do not have any control over. You have control over R0. You can make it as small as possible, so that Ez is as small as possible. So, you have control over R0. So, you can reduce the dimension, you take this dimension as small as possible. So, more important that you have a micro scale structure, and you have to have V0 small. Okay, so these are some of the factors by which you can have you can restrict the broadening of the peak. Okay, so these are some of the issues. I mean, why we are bringing in this Taylor dispersion, because there are several things in nature which are very interesting to study, but this is hurting us. So, that is why we are forced to study. Okay, so this is the problem. Now, let us get into the actual, and let us see if we can define a governing equation for this. So, I have this is the final result. This is the final result, and I may not be able to give you the exact steps all the way, but at least I will try to identify the governing equation and boundary conditions that leads to this form. But this equation, this is a very classical equation which is true for a diffusion of a spot of tracer and is true for a Taylor dispersion as well. So, you probably can have some feel for these terms, I mean, which is important. I mean, I do not expect you to remember the entire formula, memorize the formula, but at least you should develop some feeling for the terms. That's all I expect as far as this part is concerned. So, let us see what would be the governing equation in this case. What we need to do here is, if we look at this PowerPoint slide, if what we see here is this. So let me recapitulate quickly what all we talked about: Taylor dispersion and use in chromatography. So, that is what we are interested in here. Dispersion is flow plus Brownian motion is equal to rapid mixing. Example is smoke from plume carried by wind velocity. Difference between diffusion and dispersion, that you know already by now. Dispersion of tracer while flowing through a canal, circular or non-circular cross section. Microchannels are pretty much non-circular. I mean, if you have if you see how the etching is done, it is, we expect that there would be an aspect ratio and there would be an angle, because that is how the etching takes place. So, you will end up with non-circular cross section. That now, this Taylor dispersion is important when you have small transverse dimension, that means either a capillary or a microchannel. Okay. Now, what you take into account while defining the governing equation is mass transport in radial direction is by diffusion, radial direction is by diffusion, and mass transport in axial direction is by convection, because mass transport, see in the axial direction there is a flow, right. Axial direction the flow is taking place, and in the radial direction you are assuming there is no flow practically. So, in the radial direction diffusion will take place. So, that is what you take, I mean these are the components that you take to get that final result. And what we are going to see is that from the expression for the concentration profile, dispersion coefficient depends inversely on diffusivity. That means, if something is more prone to diffuse, what this means is, suppose you have a species which is likely to diffuse very fast. Okay, it is likely to diffuse very fast. Then in that case, one thing you know for sure is that this dispersion would be less. If it diffuses fast, then the dispersion would be less, because while doing the dispersion, it is basically spreading like a parabolic profile. It is spreading, but before it spreads itself, I mean, as it travels down, it is spreading more and more. But before it could spread itself, if it diffuses, Okay, so that is what is happening in this case where it is the diffusivity is more. So, and on the other hand, for 0 diffusion, the pulse will continue to distort unabated. If there is a 0 diffusion or diffusion which is negligible, 0 diffusion is not possible, then we would not be studying dispersion. But if the diffusion is negligible, if diffusion is insignificant, then the pulse will continue to distort unabated. Distort means it is first it was a pulse, it is straight pulse, then it is taking a shape, then it is going further. So, as it travels, so it will continue to distort unabated, and you expect a wide dispersion that depends on velocity. So, this depends on velocity. If you have a higher velocity, you expect this distortion to be more. For rapid diffusion, the radial diffusion inhibits the dispersion induced by axial convection. So, if there is a rapid diffusion, then the radial diffusion that takes control over, and the dispersion that is caused by axial convection, that is not taking a major role. The value of dispersion coefficient for microsystems attain value of 0.1 to 100, that is just a fact. Now, let us look at the governing equation. At least we try to write down the governing equation. We may not be able to complete this today in this class. I write this here as this is the z axis, okay. And of course, we have to work with the cylindrical coordinate, cylindrical geometry, because that would help us. So, this is what you have as r, and this is delta r, and of course, the diameter of the tube, that is defined as r 0 or something, which is the capital R 0, which is different. So, we are picking up an annular element. It is like a washer shaped element. It is an annular element which is of radial thickness delta r, okay, and this part is say delta z. All right. So, if you have this conservation of species with no generation, okay, and you are only interested in diffusion in one axis and axial convection in the other, then you would be writing it as del C del T plus u as a function of r del C del Z, that is equal to d del square C. That is a typical governing equation that you would be following. So, we talked about the axial convection and the radial diffusion. So, if we extend this form of governing equation to this case, what we get here is del C 1 del T, that is equal to minus 1 by r del r of r g 1 minus del z of C 1 V z, where G 1 is equal to minus d del C 1 del r. C 1 is we are talking about species 1, okay. We are talking about species 1 and concentration of species 1. So, this is the accumulation term on the left hand side. This is the radial diffusion term where G 1 is given here, and this is the axial convection term. So, that is what you would be getting. Okay, so, we are picking up a differential element, and if we do a mass balance, we will end up with this equation. Now, so we can write further this del C 1 del T that is equal to, if we this minus sign will cancel here, we have a minus sign already inside. So, this would be the first term would be simpler, d by r del r of r del C 1 del r. Okay. And here we have a v z term, velocity in z direction, and that there we have to introduce this parabolic velocity profile. So, what we will write here is, we will write this as 2 v naught. Why 2 v naught? Because you remember the v max in parabolic velocity profile, that v max is 2 into v average. Here the v average is referred as v 0. So, 2 v 0, 2 v naught into 1 minus small r is the any radial point, okay, and capital R 0, that is what we said is the radius of the capillary. So, this whole thing whole square. So, this gives you the v z, and since these we have already considered a fully developed flow. So, this does not have any functionality of z. So, we have taken this out here from this term, we have taken the v z out, because this is the v z we know. Okay. So, this into del C 1 del z. So, this is what we have here as the, this is the equation. Now, if we look at what the boundary conditions are, okay, we are talking about a spot of tracer here. So, at initial condition is at t is equal to 0 for all z, C 1 is equal to that Dirac function, that is m by a is nothing but pi r 0 square m by a delta z, that is at time t equal to 0 for all z, C 1 is equal to this. This is acceptable. At time t equal to 0, only you are introducing a Dirac function type pulse at the inlet. So, and at t greater than 0, see this z start, z is equal to 0 is, that is the place where the z starts. So, when you write this delta z, that means that says at t is equal to 0 for all r, you want to call it Dirac function is referred as for all z, because it is Dirac function exists only at z equal to 0. So, probably for all z, when if I write, we can write, and for all r you want to say m by pi r 0 square delta z. For all z, whether you write or whether you do not write, it does not matter, because delta z exists only at z equal to 0 and elsewhere it is all 0. So, for all z it does not matter. You want to say, you want to call this for all r. Yeah, for all r, okay. And for or t greater than 0, at t greater than 0, for r at t greater than 0, r is equal to 0 and r is equal to r 0. Can you tell me then in that case what would be the conditions here? At, okay, let me tell you, because since we are in this mode, r is equal to 0, you have del C 1 del r is equal to 0, and here also we have del C 1 del r is equal to 0. But these are completely by different for different reasons. This one is 0 because of symmetry. At r is equal to 0, this del C 1 del r equal to 0 because of symmetry, because whatever is in the upper half is same as the lower half, and this r is equal to capital R 0, there is no solute flowing out. This is basically an impermeable medium. So, that is what it says, diffusive flux at r is equal to R 0, that means at the wall the diffusive flux is equal to 0. So, these are completely by different condition. Here it is by symmetry and here it is by no flow. Okay. So, what you would do in this case is you have to define a new variable the new variable would be defined here like this. You define eta as r divided by r 0. It is a very obvious choice. I mean, why do you leave r as r, rather make r dimensionless? Everybody, I mean, everybody does it. I mean, it is very common in fluid flow with a circular cross section. And the zeta, you remember we have already said that this zeta would be equal to z minus v 0 t, and it is very obvious. I mean, you know the meaning of this numerator. You are working with a moving coordinate, and this divided by r 0, because you have to make it dimensionless. So, r 0 is the standard dimension that you have in hand. So, these are the two things that you would be incorporating in this. So, these are the two things that you would be incorporating in this, and once you incorporate them, then the equation that you get, if you replace this eta and zeta, the equation that you get upon replacement is basically d by eta del del eta of eta del C1 del eta, that is equal to z v 0 r 0 half minus eta square del C1 del zeta. That is what you will end up with. That is what you will end up with if you substitute these eta and z, if you substitute these two terms r and z by the zeta and zeta, and a solution of this above equation that satisfies, I mean, a solution of this above equation which satisfies the boundary conditions which you have already specified is given as C1 is equal to C1 at eta is equal to 0 plus 1/4 V naught R naught by d del C1 del zeta at eta is equal to 0 into eta square minus half eta to the power 4. This is considered a solution to this equation that satisfies the boundary conditions described before, and then you calculate the average concentration, because this C1 as a function of R and Z does not make any sense, because you are not going to measure it with reference to R, neither you are going to express it. So, what you are interested in is something called a C1 bar Z only. So, it is averaged over the entire cross section R, and that would be equal to 1 by pi r 0 square integration 0 to r 0 2 pi r C1 r z, C1 as a function of r z dr. So, basically you are picking up an annular element, and that annular element will have an area 2 pi r dr, okay, and you are multiplying each such annular element with that corresponding concentration C1 r z and integrate it between 0 to r 0, and finally you divide this area pi r 0 square to get an average concentration over the entire, the concentration averaged over the entire cross section. So, this is a very common way of, I mean, you have already found out average velocity using this method. You remember when you work with this parabolic velocity profile, if you are given a parabolic velocity profile and if you are asked to find out what is the average velocity, this is exactly what you do, 2 pi r dr into u and integrate it. So, this is exactly what you are doing here. So, this is equal to, you can see a lot of things are cancelling out, and you would be ending up with 2 integration 0 to 1 eta C1 d eta. This is what is the C1 bar z, that is equal to C1 bar z. I have some amount of work left, probably it will take some 5 or 10 minutes maximum, and then we will be done with this derivation. I mean, at least essentially I will jot down all the steps that would lead to this final form what we have here, because our aim is to get to this final form. This is the final form. Only thing is, this is a form we are already familiar with for a spot of tracer diffusing into an infinite medium. Only thing is, we are not familiar with this Ez term, and how we ended up with this Ez term, that is what we are curious about. Of course, this is the, you have to keep in mind that this Ez is R0 V0 square by 48D. Now, if you have a non-circular channel, you will have a different such formula. There it would be a very similar one, square divided by some number. Instead of 48, you will have some other number and d. So, that also we will touch upon. So, probably I will take 5-10 minutes of next class, first part of the next class, to wrap this up, this stellar dispersion. Okay. Once this stellar dispersion, and I will also discuss a little bit of I mean, if you bring in the chromatographic effect, because we are this derivation that we are working with is basically just the radial diffusion and axial convection. We have not talked about any chromatographic effect here, but if you introduce a chromatographic effect, okay, if you introduce a chromatographic effect by which some solute is held up at the wall by adsorption and then it is released. So, what would be the I mean that I cannot derive, that is beyond the scope of this class, but I will give you the final expression and expect that you will appreciate the individual terms. And once that is done, next topic that we pick up is electrokinetics. We will be talking about this electroosmosis and electroosmotic flow and all this. So, that would be probably by end of next class or next class we should be in electroosmosis. We will be done with mixing and dispersion. That is all I have for today's class. Thank you very much.